Ever wondered how models like ChatGPT or Google Search understand your language so well? In this video, we'll break down one of the most revolutionary models in natural language processing, BERT, and even show you how to implement it from scratch using PyTorch. BERT stands for Bidirectional Encoder Representation with Transformers. To put it in simple words, BERT extracts patterns or representations from the data or word embeddings by passing it through an encoder. The encoder itself is a transformer architecture that is stacked together. It is a bidirectional transformer, which means that during training it considers the context from both left and right of the vocabulary to extract patterns or representations. BERT uses two training paradigms, pre-training and fine-tuning. During pre-training, the model is trained on a large dataset to extract patterns. This is generally an unsupervised learning task where the model is trained on an unlabeled dataset like the data from a big corpus like Wikipedia. During fine-tuning, the model is trained for downstream tasks like classification, text generation, language translation, question answering, and so forth. Essentially, you can download a pre-trained model and then transfer-learn the model on your data. The benefit of the transformer architecture is that it helps the model to retain infinitely long sequences that were not possible from the traditional RNNs, LSTMs, and GRU. But even from the fact that it can achieve long-term dependencies, it still lacks contextual understanding. BERT falls into a self-supervised model. That means it can generate inputs and labels from the raw corpus without being explicitly programmed by humans. Remember, the data it is trained on is unstructured. BERT was pre-trained with two specific tasks, masked language model and next sentence prediction. The former uses masked input like the man, mask, to the store instead of the man went to the store. This restricts BERT to see the words next to it, which allows it to learn bidirectional representations as much as possible, making it much more flexible and reliable for several downstream tasks. The latter predicts whether the two sentences are contextually assigned to each other. For instance, if sentence A is CLS, the man, mask, to the store, and sentence B is penguin, mask, are flightless birds, SP, then BERT will be able to classify whether both the sentences are continuous or not. During the training, BERT uses special types of tokens like CLS, mask, SP, etc. that allow BERT to distinguish when a sentence begins, which word is masked, and when two sentences are separated. BERT can also be used for feature extraction because of the properties we discussed previously and feed these extractions to your existing model. Let's understand with code how to build BERT with PyTorch. We will break the entire program into 4 sections. 1. Pre-processing, 2. Building model, 3. Loss and optimization. For training. Pre-processing. In pre-processing, we will structure the data such that the neural network can process it. We start by assigning a raw text for training. Then we will clean the data by making the sentences into lowercase. Creating vocabulary. Vocabulary is a list of unique words in the document. Now, in the following step, it is important to remember that BERT takes special tokens during training. Here is a table explaining the purpose of various tokens. CLS, the first token, is always classification. SCP separates two sentences. YND and the sentence. PAD, used to truncate the sentence with equal length. Mask, used to create a mask by replacing the original word. These tokens should be included in the word dictionary, where each token and word in the vocabulary is assigned with an index number. Once that is taken care of, we need to create a function that formats the input sequences for 3 types of embeddings: token embedding, segment embedding, and position embedding. What is token embedding? For instance, if the sentence is "the cat is walking," "the dog is barking," then the function should create a sequence in the following manner: CLS, "the cat is walking," SP, "the dog is barking." After that, we convert everything to an index from the word dictionary. So the previous sentence would look something like 1, 5, 7, 9, 10, 2, 5, 6, 9, 11. Keep in mind that 1 and 2 are CLS and SP respectively. What is segment embedding? A segment embedding separates two sentences from each other, and they are generally defined as 0 and 1. What is position embedding? A position embedding gives position to each embedding in a sequence. We will create a function for position embedding later. Now the next step will be to create masking. As mentioned in the original paper, BERT randomly assigns masks to 15% of the sequence. But keep in mind that you don't assign masks to the special tokens. For that, we will use conditional statements. Once we replace 15% of the words with mask tokens, we will add padding. Padding is usually done to make sure that all the sentences are of equal length. For instance, if we take this sentence, the cat is walking, the dog is barking at the tree, then with padding, it will look like this. CLS, the cat is walking, pad, pad, pad. CLS, the dog is barking at the tree. The length of the first sentence is equal to the length of the second sentence. Since we are dealing with next word prediction, we have to create a label that predicts whether the sentence has a consecutive sentence or not, i.e. is next or not next. So we assign true for every sentence that precedes the next sentence, and we use a conditional statement to do that. For instance, two sentences in a document usually follow each other if they are in context. So, assuming the first sentence is a then the next sentence should be a plus 1. Intuitively, we write the code such that if the first sentence positions i.e. tokens underscore a underscore index plus 1 equals tokens underscore b underscore index, i.e. second sentence in the same context, then we can set the label for this input as true. If the above condition is not met, i.e. if tokens underscore a underscore index plus 1 equals tokens underscore b underscore index, then we set the label for this input as false. BERT is a complex model, and if it is perceived slowly, you lose track of the logic. So, it'll only make sense to explain its component by component and their function. BERT has the following components: embedding layers, attention mask, encoder layer, multi-head attention, scaled.product attention, position-wise feed-forward network. BERT, assembling all the components. Embedding layer. The embedding is the first layer in BERT that takes the input and creates a lookup table. The parameters of the embedding layers are learnable, which means when the learning process is over, the embeddings will cluster similar words together. The embedding layer also preserves different relationships between words such as semantic, syntactic, linear, and since BERT is bidirectional, it will also preserve contextual relationships as well. In the case of BERT, it creates 3 embeddings for token, segments, and position. If you recall, we haven't created a function that takes the input and formats it for position embedding, but the formatting for token and segments are completed. So we will take the input and create a position for each word in the sequence. And it looks something like this. In the forward function, we sum up all the embeddings and normalize them. Creating attention mask. BERT needs attention masks, and these should be in a proper format. The following code will help you create masks. It will convert the pad to 1 and elsewhere 0. Encoder. The encoder has 2 main components: multi-head attention, position-wise feed-forward network. The work of the encoder is to find representations and patterns from the input and attention mask. Multi-head attention. This is the first of the main components of the encoder. The attention model takes 3 inputs: query, key, and value. Multi-head attention takes 4 inputs: query, key, value, and attention mask. The embeddings are fed as input to the query, key, and value argument, and the attention mask is fed as input to the attention mask argument. These 3 inputs and the attention mask are operated with a dot product operation that yields 2 outputs: context vectors and attention. The context vector is then passed through a linear layer, and finally that yields the output. Now let's explore the scaled product attention. The scaled product attention class takes 4 arguments: query, key, value, and attention mask. Essentially, the first 3 arguments are fed with the word embeddings, and the attention mask argument is fed with attention mask embeddings. Then it does a matrix multiplication between query and key to get scores. Following that, we use scores. Masked underscore fill underscore attention underscore mask -1 times 10 to the power of 9. This attribute fills the element of scores with -1 times 10 to the power of 9, where the attention masks are true while the rest of the elements get an attention score, which is then passed through a softmax function that gives a score between 0 and 1. Finally, we perform a matrix multiplication between attention and values, which gives us the context vectors. Position-wise feed-forward network. The output from the multi-head goes into the feed-forward network, and that concludes the encoder part. Let's take a breath and revise what we've learned so far. The input goes into the embedding and as well attention function, both of which are fed into the encoder, which has a multi-head function and a feed-forward network. The multi-head function itself has a function that operates the embeddings and attention mask using a dot product operation, assembling all the components. Let's continue from where we left, i.e. the output from the encoder. The encoder yields two outputs, one which comes from the feed-forward layer and the attention mask. It's key to remember that BERT does not explicitly use a decoder. Instead, it uses the output and the attention mask to get the desired result. Although the decoder section in the transformers is replaced with a shallow network which can be used for classification as shown in the code below. Also, BERT outputs two results, one for the classifier and the other for masked. Few things to keep in mind. You can assign the number of encoders. In the original paper, the base model has 12. There are two activation functions, TAN and GELU, Gaussian error linear unit, loss and optimization. Although the original paper calculates the probability distribution over all the vocabulary, we can use a softmax approximation. But a neat way to do it is to use cross-entropy loss. It's a combination of both softmax and negative log likelihood. So, while building the model, you don't have to include softmax, instead get a clean output from feed-forward neural nets without softmax normalization. When it comes to optimization, we will be using Atom Optimizer. Training. Finally, we'll start the training. So, that was BERT coding from scratch. If you train it over a large corpus, you can use the same model for pre-training. Use any corpus, but with the exact format of input representation as mentioned before. Fine-tuning. Make sure that you use supervised learning data for it. Feature extractor for different tasks, or even topic modeling. Is there a way to get a pre-trained model? In the original paper, two models were released, BERT Base and BERT Large. In this video, I showed how you can code BERT from scratch. Generally, you can download the pre-trained model so that you don't have to go through these steps. The Huggingface library offers this feature. You can use the transformer library from Huggingface for PyTorch. The process remains the same. I have a notebook linked in the description where Nilesh Barla used a pre-trained BERT from Huggingface. You can check it out in the description. When you use a pre-trained model, all you need to do is download the model and then call it inside a class and use a forward method to feed your inputs and masks. Final thoughts. BERT is a very powerful state-of-the-art NLP model. The pre-trained model is trained on a large corpus, and you can fine-tune it according to your needs and based on the task on a smaller dataset. The best thing about fine-tuning is that you don't do it for 1,000 epochs. It can mimic SOTA performances even in 3 to 10 epochs, depending on the parameters and how well the dataset is processed. Until next time, keep learning and coding.